Thank you very much, Jens, for the kind introduction. Let me remove the echo here. And apologies for not being able to make it there. I'm sandwiched between travel and my class tomorrow. I came back from Micro and Pact, which was in Chicago just today, actually. So sorry for not being able to make it. I understand we have an hour. I somehow thought that we had 2 hours. I have a lot of slides on this talk, but we're not going to cover all of them, I think. And feel free to ask questions in the middle too. So I'm going to talk about memory-centric computing. And I think everybody in this room and this conference agrees with the statement that computing is bottlenecked by data. And data is really key for many applications. All important workloads are data intensive. They require increasingly sophisticated analyses on the data. And on top of this, data is increasing. We can generate more data than we can process. This has enabled certainly a lot of interesting things, but it's also causing a lot of trouble in the way we design our systems. And this is an example, neural networks. A lot of you may be working on it. This is a nice talk by Cerebrus's chief architect. They're designing wafer scale processors so that they can put memory and compute together on the same chip, 40 gigabytes of SRAM with a lot of computation. You can take a look at that and look at this talk. But basically, the takeaway is that compute requirements are growing overwhelmingly. At the same time, memory requirements are growing overwhelmingly as well. But this is not new, in my opinion. I mean, there are many other applications that are very much data bound. And there are some examples over here. Data poses a big performance energy bottleneck in them. And there are many applications on the mobile end also that are data bound. And we're going to look at these applications later on as well. Data is a big performance energy bottleneck for them. And as was mentioned, I do a lot of work in bioinformatics, and especially genome analysis and acceleration of genome analytics. And this is an area where data is really exploding truly. And the reason is our technologies are becoming much better. So genome sequencing technologies have become much more sophisticated and much less costly over decades, as you can see over here. This is the cost of sequencing genome. It's been reducing much faster than Moore's law has enabled us to reduce the cost of a transistor. As a result, we're able to sequence genomes a lot faster at a lot higher throughput. Now, the problem is we want to do analyses on these genomes, scientific discovery, medical advancements, etc. Unfortunately, we're really bottlenecked by how fast we can move the data and how much analysis we can do on the data relatively quickly. So technology, sequencing technology is not the bottleneck, basically. Our bottleneck is really computing. And there are clearly many answers we can get with genome analysis. COVID-19 is a great example, in my opinion. These genome sequences that I'm going to show you have been used in COVID-19, not just outbreak detection, but also analyses of different variants. But there's a lot more you can do with genome analytics. And this is an example of a data generator. This small device is a great data generator. It's about $1,000 or so, and you can buy it and you can generate data. But unfortunately, to be able to do some interesting analysis on the data, you have to move the data outside. Not even a laptop is enough. You have to move it to the data centers today. So basically, we're churning a lot of data all around the world, both at the macro scale as well as the micro scale. In this talk, we're going to look at especially the micro scale, but maybe we can do a lot of things at the macro scale for minimizing data movement, like pushing computation to the sensors, edge devices as much as possible so that we can minimize the issues that data generate for us. Okay, so I think the overall picture that I would like to discuss is we have very special purpose machines for data generated today. They're specialized, they're fast. Genomics is one example. Video is another example. Internet is another example. We have a lot of clicks, for example, that are being generated, a lot of information. But we're feeding this data to far away general purpose machines, which is really overwhelming the systems we design, in my opinion, today. And this picture is really similar to many data generators and analyzers. And genomics is something that we're working on a lot. I'm not going to talk a lot about it, but I'll leave you with some papers if you're interested. We've written this long article that essentially is an introduction to genome analysis. You can take a look at it. And I will mention one work that we have done recently. This is not even with using existing devices. Basically, today you can buy FPGAs with high bandwidth memory, and you can offload computation to those FPGAs that have high bandwidth memory. Essentially, you have FPGA logic, a configurable logic that has low latency, high bandwidth access to reasonably large amounts of memory. And if you can do the offloading, we did this work together with IBM. So we used IBM Power 9 CPUs and used their relatively coherent interface. I think of this as a predecessor for CXL, for example, or CAPI, so that you can offload weather modeling as well as genome analysis applications, and we configure the logic inside the FPGA so that it can maximize the use of the memory. And if you do that, even today, you can get significant performance and energy improvements. And this is, you can see the numbers over here, but I don't want to focus on the numbers. But basically, you can get large performance energy improvements at the same time without, because you eliminate data movement, as well as specialize the logic that you design for the purpose of the application. So this is just one example. This is clearly more memory-centric than existing system. Instead of moving everything to an IBM Power 9 CPU, we're moving it to the FPGA that's more tightly coupled with memory. What I'm going to talk about in this talk is going to be even more memory-centric. We're going to couple execution units right inside the DRAM chip, for example, or we're going to use the analog computation capability of the DRAM chip or other chips so that we don't even actually need to build execution units. We just do computation using the analog domain. Okay, but just to motivate you, these are some examples with what you can do today, with some pain, of course. And there are other things that you can do. We've been looking at genome analysis, and these are very interesting works, in my opinion. For example, I'm going to talk about this one. In storage, you can accelerate genomics with some simple filtering mechanisms, but we'll get back to it later. And the applications are becoming more sophisticated in terms of genome analysis. Normally, you would think of, you'd have a single linear genome, and you would do the mapping when you sequence the reads to a single linear genome. But today, genomes are also graphs. So you're really doing a mapping of what you sequenced from your DNA, for example, to a huge graph. So the application is becoming bigger and more sophisticated as well. Accesses are becoming more irregular. And the future is not going to be better. Basically, we're going to generate a lot more data. So we need to somehow figure out how to cope with it. If you're interested in genome analysis, I can talk more about it, but unfortunately, I'm not there, so we will not be able to talk in person. But this is just one example. I think there are many, many other application domains that are interesting. And essentially, our machines are being overwhelmed in terms of their storage, communication, and computation capability. And if you go back to the fundamentals, we do need three components in our system: computing, communication, and memory and storage. And if you look at the history of computing, we've essentially focused on computing units overwhelmingly. Everything else is mostly ignored. I think we should not be ignoring them. We should be able to do computation in everything that we design in our system, as opposed to moving everything to the computing unit. So this is a cartoonish picture of the computing unit that we have. This is a single node. And if you look at this, most of the single node is dedicated to storing and moving data. Computation is done only in the red parts, the cores over here. Everything else is there to store and move data: caches, interconnects, other caches, other interconnects, memory controls, other interconnects, other caches, main memory, other interconnects, storage, other interconnects, basically. So if you do the calculation, more than 95% of a single node is dedicated to structures that cannot compute, but that can store and move data. Yet, our system is still bottlenecked by those structures, meaning memory. And if you don't believe me, these are real pictures from real chips. This is AMD. You can see this box over here, this green box, shows the L3 and L2 caches. It doesn't even show everything else. So this box over here is the global memory interconnect. And basically, essentially, most of the chip is for memory and storage. And they're adding still more caches, another die for caching. Is that going to be useful? Is this the right thing to do? Well, clearly, it's good for business, but is this the right thing to do for energy, sustainability, and really, truly getting the high performance out of our systems? That's very questionable, as we will see. This is IBM Power 10, not to pick on AMD. So clearly, other systems are like this. This is Apple. I think of the computing chip as just a lot of SRAM memory, and the rest is a lot of DRAM. And there's the darkness over here, which is the storage. And these are all darkness because they cannot do anything to the data. They have to move the data to the very small amount of logic in the processor or the accelerators, basically. And even though we're dedicating a lot of our resources, we're still bottlenecked by the memory system. And this is one study that we did with Google a few years ago. We analyzed the workloads that I showed you in the prior picture in the mobile devices. And we found out that more than 60% of the total system energy is spent on data movement, solely moving the data across the memory hierarchy. We don't even have storage examined in the system because we're assuming everything is inside the main memory. Now, if you add storage to it, this number grows actually. Actually, this number already grows depending on the workload you examine. In some workloads, in some neural network workloads, even though you're doing inference, for example, in short-term memories, because your accelerators are not good enough and big enough, more than 99% of the total system energy is spent on moving data across the memory hierarchy to feed the accelerator. So this number is actually going to grow. So my axiom going forward is going to be an intelligent architecture needs to handle data well. And we're hopefully designing intelligent architectures. These architectures will be making decisions for us. The question is, how should we really design them? Let's say 10, 20 years down the road. So how do we handle data well? I think there are three major directions. I'm going to focus on the first one. I'm just going to mention the second and third one briefly because they're synergistic and they're important, but unfortunately we don't have time. The first one is really memory-centric computing. We should ensure that data doesn't overwhelm the components by designing algorithms, architectures, and systems together so that data doesn't overwhelm us. The second one is, today we're designing our systems, architectures, hardware and software to make decisions. Some of them are making memory controller decisions, for example, power management decisions, etc. Are they really taking advantage of data to make intelligent decisions, or are they really making decisions based on some human designer dictated them? And today we're mostly doing the second one. A human designer dictates the policies that are employed by our controllers. As a result, those policies are usually very, very suboptimal on a given workload and on a given operating condition. So for example, the memory controller makes decisions based on the human designer's thinking, as opposed to taking advantage of past things that it may have learned. So we need to move to more learning-based decision-making, as opposed to human designer dictated decision-making. More data, we should basically have more data-driven decision-making. Unfortunately, I don't have time to talk about it, but we're doing a lot of work on, for example, using reinforcement learning and machine learning to design hardware controllers that can adapt to the workloads much better. And we see significant performance benefits in terms of data placement, for example, or prefetching, memory scheduling, or even bypassing the cache hierarchy when you're not going to hit in the caches. And the third direction is we should probably be taking advantage of the properties of the data better in our systems. Today, when we actually present some sort of data to our system, when we read, for example, from memory, we don't really take into account the properties of data. Whereas data has a lot of properties, right? It has quite clearly performance properties. It has approximability properties, security properties, privacy properties, compressibility properties. This information doesn't get communicated or even found out at the hardware and software levels, various ones. And then in the end, we make decisions that are just structural. For example, a memory controller, when it's trying to prioritize one request over the other, or a storage controller, pick any of the controllers, when they're trying to prioritize one request over the other, they don't ask the question, oh, is this security critical? Or is this really latency critical for me? Is this quality of service critical? This information doesn't get communicated. As a result, they make decisions based on the structures of DRAM. Is this request going to hit in the row buffer? If it's going to hit in the row buffer, let me try to maximize my DRAM throughput. Is that the right thing to do based on the characteristic of the data you're accessing? We never question that because we don't even know that information. So I think going forward, we need to make our architectures much more data aware or data characteristic aware. I spent a lot of time on this slide because I think this is really how we, it gets into the guts of how we handle data. I think going forward, we should be much more data centric. I'm going to talk a lot about that, but also more data driven in terms of our decision making in our systems, and also much more data characteristic aware, as opposed to making decisions just based on components. Because in the end, what matters is data, right? And we're doing a lot of analyses on the data, and our goal is to really figure out what's going on with the data, not with the components of the system that are making decisions. Okay, so but in the end, I think we'll need to rethink the entire stack to be able to do all of this in the best way. But I will hopefully show you some examples, at least from the data-centric perspective, that we can get there step by step. But you can read papers that describe the vision that I just outlined, that I just mentioned. So let's jump into the first part of it, which is what we're going to cover essentially. And then I'm going to give you a choice, because since we don't have a lot of time today, and I don't want to be standing between you and dinner. So let's jump into data-centric architectures. Even if you look at data-centric architectures, there are a bunch of properties that we really want from a system to be data-centric. First of all, I think we should enable processing across many parts of the system, all parts of the system, and enable people to process data where it makes sense, as opposed to being forced to bring the data to a compute unit, which may be a CPU, GPU, accelerator, whatever it is. We also need to rethink our memory hierarchies to have low latency and low energy. And I think there needs to be a lot more innovation in this area. We have these very good conventional technologies, which I'm going to talk about, but we need other technologies that are low latency and even lower energy going into the future. And low-cost data storage and processing is clearly important, and there are many ideas we should employ over here, and we should intelligently manage data. Okay, so I'm going to again focus on the first part because we don't have time for everything else, and we're going to jump into processing data where it makes sense. And I will present this picture to you again, Processing data where it makes sense to me that means that we should enable processing capability everywhere in the system that you see, including the sensors over here, as opposed to forcing ourselves to bring data into the very small amount of computation units. And this is not a new idea. People have thought about this since 1960s, and people have written nice papers about it. These are some earliest papers in terms of logic in memory or processing in memory. If you know of some other papers, please let me know. These are beautiful papers. And clearly, people have looked at this, and it has not been successful. Why should we have hope today? I think today we're having huge problems with memory technology, in particular DRAM technology. Earlier, Jens mentioned Rowhammer. I'm going to very briefly mention that. But basically, memory technology scaling is not going well. We're having a lot of trouble in terms of our memory technology. As a result, we need some computation capability close to memory to fix those issues. And this is already happening. People are adding inside the DRAM chips some access counters to figure out which rows are being accessed a lot, and some intelligence to make sure that those rows are not accessed too much so that you don't get bit flips in memory. This is one example. Error correcting code is another example. And this is going to be increasing the trend. Flash controllers already have this. And there's a huge demand from applications and systems that we've never experienced before, which is going to get worse. We have a huge data access bottleneck, energy and power are key bottlenecks, and data moment energy dominates computation energy. So we're going to examine these. And at the same time, I think in human history, we never needed performance, energy, and sustainability at the same time. Basically, we do not want a trade-off anymore, in my opinion, especially if we consider sustainability in the world. We don't want to increase performance at the expense of energy. We want to increase performance while reducing energy. The question is, how do we do that? And I think data-centric computing can enable that, as I will show you with some real results. So basically, today our designs are squeezed in the middle. Memory technology is squeezing us to have intelligence. Application systems are telling us to have something different in our paradigm. So let's take a look at what's the processing in memory landscape today based on this. Basically, if I was giving this talk a few years ago, I would be showing you these technologies. These are 3D stack technologies. They're beautiful. You have logic layer underneath memory layers, and you have high bandwidth, low latency connections to the logic layer. Inside the logic layer, you can do any computation. That's great. And people have been looking into this. I think there will be more of this. Micron has been experimenting with this technology. But 3 years ago, some of these, well, none of these existed. So UpMem, for example, is a startup in France where they put processing capability inside the DRAM chips. We may talk about that depending on how time goes. Essentially, this exists today. Samsung introduced machine learning accelerators inside the DRAM chips, high bandwidth memory chips. SK Hynix introduced similar machine learning accelerators in GDDR6. Samsung, together with Meta, Facebook, introduced DRAM modules that look like this for improving recommendation inference, performance, and energy. And Alibaba essentially did the same thing for the same purpose, except they didn't do a module. They put the processing capability inside the DRAM chip. So essentially, processing in memory is happening, at least at a prototype level today. Hopefully, it will happen more and more. And the reason is basically what I said earlier. Well, I should also say that there are many other experimental chips and startups that are doing things that are not fitting on the slide, but there are tens of them. If you're interested, I'd be happy to talk about them. So this is happening because we have technology problems as well as application problems. Let me talk about the technology problems very, very quickly. Because we're having a lot of technology issues, industry has opened up to have new memory architectures. This was not possible, let's say, 10 years ago. Today, industry is actually looking at new memory architectures. And we've been motivating this about 10 years ago or even earlier. We've been claiming that memory technology scaling issues are going to get worse and worse. If you're interested, there are papers. And this is actually one thing that I used to motivate these issues. This is data that we obtained together with Facebook around 2013. We published a paper in 2015. But this basically shows a correlation between the chip density employed in a Facebook server. And there are a lot of servers that are participating in this study. This is on production data centers. This is DRAM chip density. Sorry, somehow. No. Yeah, this is DRAM chip density on the x-axis. And the relative server failure rate, basically due to memory errors. You can see that there is a very strong correlation because denser chips have cells that are smaller and closer to each other. As a result, they're more error prone. And as a result, this is reflecting itself in the system level. And if you're interested, there's more in our paper, but I don't have time to cover that. So we actually did a lot of studies to understand such issues at a lower level. What are the memory errors happening? Can we prevent them? Can we fix them? What do we do to fix them? In the end, everything points to intelligent memory controllers. So these are some example infrastructures that we have developed to test DRAM. And as was mentioned earlier, we did a lot of studies on Rowhammer. And this is the fact that you can predictably induce errors in most DRAM memory chips. I think this is an indicator of how bad memory technology scaling issues are. These are not my pictures. I just borrowed them. But basically, I'll tell you briefly about Rowhammer to show you that issues are not going to get better. Essentially, when you apply high voltage or activate a row, read a row in DRAM, you apply high voltage to the word line. Now, if you actually want to read some other row, you need to apply low voltage to that word line. Now, if you keep doing this repeatedly, for whatever reason, you could do this in a real program, actually, user level, and people have done this many times. Adjacent cells and physically adjacent rows get corrupt. And this clearly should not be happening because you're not even writing to those rows. You're not even writing to any place in memory. Basically, you're causing data corruption. And this is happening in more than 80% of the chips that we've tested from 3 major manufacturers. There are only 3 major DRAM manufacturers in the world. And the problem is actually much worse, as we have shown in recent works that I'm not going to talk about. Essentially, this could also be, this is not only a reliability problem, but this could also be exploited as a security problem. And security community has been doing a lot of interesting work to show that this is a big problem. And also, people are doing work on fixing it also. But I'm not going to talk about it. That's a subject of a totally different talk. If you're interested, there are talks out. And if you're interested, a very 20-minute summary of it, I'd be happy to give it at some point. But this is an example of memory scaling issues. And these are real. They're going to get worse. And there are a lot of papers written about it. This is something that we wrote, that we were invited to write in 2019, if you want to get into Rowhammer relatively quickly. So that's one example. Another example of technology scaling is DRAM technology scaling is not going well. Why not have other memory technologies? Potentially they're based on DRAM also, and put them together in a heterogeneous memory hierarchy. And these memory technologies have different greens and different reds. And then you design the hardware and the software to maximize the greens of each technology as much as possible, while avoiding the reds of each technology as much as possible. Sounds great. This is already happening, actually. If you look at modern GPU-based systems and heterogeneous systems, they have heterogeneous memories also. And not necessarily phase change memory today. I think in the future, there might be other technologies going forward also. We may have a lull for some time, but I think the future of emerging memory technologies that are non-DRAM based is going to be very interesting also. But basically, if you look at a hybrid memory system like this, this enables better scaling of the memory as well as the entire system, but it requires intelligence from the memory controllers. Memory controllers now need to understand the characteristics of the devices as well as the software and communicate between them. So this is also pushing for more intelligence on the memory side. This is an example solution that is being proposed for solving Rowhammer, and that requires intelligence in the memory controller. And industry is also writing papers about it too. This is a paper that was written by Samsung and Intel. This is the only paper that I know of that was written by these 2 companies. Otherwise, these companies don't even talk to each other without lawyers. Maybe a huge lawyer teams. But basically, they say essentially the same thing in 2014. DRAM is not scaling very well. We should really have intelligent controllers fixing these issues. And there are other examples of intelligent controllers that I'm not going to talk about that can identify uncorrectable errors in memory chips also. So if you actually put some intelligence on the memory system, you can identify errors that are not, that you couldn't even correct before. And we know actually how to build intelligent memory controllers. Some of you over there may be doing storage. Storage system has very intelligent memory controllers to make sure that these errors are not happening. We've done a lot of work on storage. If you're interested, I'm happy to at some point talk about it. But essentially, there are a lot of techniques that are employed in intelligent controllers that are inside the storage system to ensure that we don't get bit flips, for example, and many other things as well. So I think the main memory is going to go the same way. We're going to put more intelligence. And people have asked the question in the storage system also, can we actually put intelligence into the storage system? Can we actually offload applications? And we've been doing the work in that area. Others have been doing work. Offloading applications to the storage system actually has a lot of benefits. That's true for main memory as well. Now you can say, okay, these issues, if you come up with a new memory technology, they're not going to exist. Unfortunately, we don't know of any memory technology that doesn't have these issues. All memory technologies, as they scale to very small node sizes, are going to have this problem. And when I talk about memory, I also talk about storage. Actually, for me, memory and storage are the same. In the end, they're all cells that store data in some form. So basically, unfortunately, we need intelligent controllers for other memories too. I think going forward, we cannot get away from intelligent controllers because they're going to help us in many ways. So that's the push from circuits and devices. Now let me jump into the push from applications and systems. And this is actually going to be even stronger, in my opinion. And in my opinion, we have a bigger responsibility here. Do we want a world that looks like this, where we waste a lot of energy, where we save a lot of energy? Or do we want a world that looks like this? I would argue that we want a world that's sustainable, livable, energy efficient, but we also want high performance all at the same time. As I said earlier, we do not want a trade-off between these things. And I think the problem is today we're designing our systems based on some principles that lead to great energy waste. Essentially, we're moving data all around. Between the, let's say, even if you take the memory and the processor, we're moving data between the memory and the processor constantly. And you can extend this to the storage system, you can extend this to the tape, you can extend this to the global data generation and data analysis capability that we have in our planet, let's say. So we know that this is causing great performance loss. So we actually complicate our systems more. We add a lot of techniques at the hardware and the software to overcome the performance loss as much as possible. We add heavy levels of multi-threading, out-of-order execution, many levels of redundancy, and what else? Prefetching, many levels of caching. And this is actually increasing the complexity as well as the energy waste in our systems. Basically, all of these hierarchies and techniques, when they work, that's good, but they don't always perfectly work. And many of the time, they don't even work. There are some random access applications where none of these techniques work at all. As a result, they're compounding the energy waste. So we're in a vicious cycle, basically. We want to overcome the performance loss. There's a fundamental energy waste because of data movement. We want to overcome the performance loss because of it, but we're wasting even more energy by adding complexity to our systems, and our techniques do not work. So I think we should somehow break the vicious cycle, if for nothing else, for the sake of the planet, if you will. But the vicious cycle is only broken if we really understand what's going on. Basically, the problem, I believe the real problem is processing of data is performed far away from the data, and that's causing us to go into this vicious cycle. So let's go back to this picture. We are basically processing all data in the processor at great system cost, as well as at great application cost and energy cost. Yet we know that this is a problem. I mean, it's not like we don't know memory is the limiter. This is actually a beautiful one-page paper that was written by Dick Seitz, who was the chief architect of Alpha architecture in 1990s. After their team designed the Alpha architecture, he basically wrote this paper saying that we designed this great processor. It's capable of finishing 4 instructions every 1 clock cycle. Unfortunately, on this important workload, it's a database workload that we designed this processor mainly for, it's finishing 1 instruction every 4.5 cycles. So basically, it's operating at 1/18th of its peak efficiency. And he concludes this paper by saying, I expect over the coming decade, memory subsystem design will be the only important design issue for microprocessors. This is 1996. Fast forward about 10 years, this is my data from my own PhD thesis. Basically, together with Intel, we showed essentially the same thing. Most of the time, the flagship processor is waiting for cache misses to finish. Okay, if you don't believe me, if you don't believe Dick Seitz, this is data from Google, since everyone believes Google. This is their beautiful ISCA 2015 paper, where they showed essentially the same thing. Most of the time, the processor is waiting for data across all of their data center applications, according to them. And that's a nice paper. So basically, we have a problem with the processor-centric design. Even though the processor is improving performance, it's grossly imbalanced. Data moves a lot, and this energy inefficient, low performance, and complex, and we're overly complicating our systems as well. As a result, we're back to the picture that I showed you earlier. Most of the system is dedicated to storing and moving data, yet the system is still bottlenecked by memory in terms of performance. So that was performance. Let's look at the energy perspective. This is even worse. This is data from Bill Daly from 2015. You can argue with all of the numbers, but the relative differences you cannot argue with. So basically, 64-bit double precision floating point operation, 20 picojoules with some technology parameters. This is a complicated arithmetic operation. A DRAM read or write, 16 nanojoules. That's 800x difference. So imagine how much locality you need to have in your caching to overcome the energy differential that you see over here. Basically, you need to be able to reuse the data pieces that you're bringing to do that piece of computation many times. Also, you're going to write the data back at some point. So think about that to overcome this huge energy differential. So if you want to get an energy equivalent point with processor-centric and data-centric system, this picture is good to think about. Okay, that was a complicated operation. What about a simple arithmetic operation, just a 32-bit integer addition? The difference between a DRAM read or write is 6,400 times. So the question is, does it really make sense to bring 2 pieces of data to do a 32-bit arithmetic operation and write back the data again and consume 3 times 6,400x the energy of the addition that you're bringing data for if you don't have good enough locality? And most of the time, you don't have this amount of locality, especially in emerging applications. Okay, I'm going to skip some of these slides, as I said. As a result, we have this picture basically. Most of the system energy is spent on data movement, and 60% is a low number, in my opinion. So I would argue that we do not want to move data. We want to have a new paradigm where it can enable computation with minimal data movement, compute where it makes sense, where data resides, as opposed to just in the processor or the accelerator. We want to make computing architectures much more data-centric. So this is easier said than done, of course. And I believe we need to re-examine every single place where data resides or is generated and enable computation capability over there and be very judicious and opportunistic about it. I'm going to talk about memory and slightly storage after this point. Memory is very interesting because we bring a lot of data and store it there for a long time. And clearly people have optimized their system so that they can have in-memory databases, in-memory graph processing, in-memory media processing, in-memory machine learning increasingly. So we would like to be able to communicate with memory and tell the memory, can you do this computation for me? And the memory does the computation and returns the results. Now, it's nice, but this requires a lot of changes to the memory, controllers, processors, and communication units, software and hardware interfaces to enable this, system software compilers and languages to make this easier on the programmer, and algorithms should be redesigned or rethought so that it can better fit the computation capabilities that are out in the memory. And even theoretical foundations of the computing should be revisited. So clear this is an across the stack problem. I would mention the theoretical foundations because I'm assuming everybody over there has taken an algorithmic complexity course, or some of you are maybe teaching it. When you're doing that, you're really counting operations, right? But we just showed that operations don't matter as much. In terms of energy and performance, it's really the data movement that matters. We need a more data-centric theory of computing going forward, in my opinion. So I'm going to now focus on some techniques and give you some hope and results. But we actually release this paper, and we keep updating this paper online on archive. If you're interested, this covers a whole lot more than I can cover in the remaining amount of time. And before I do that, I've also mentioned that we have a processing in memory course that we keep teaching, and anyone who's interested in it would be willing to attend or contribute. I would also mention that we need to think differently from past approaches. I will classify processing in memory into two different ways of doing it. And after this, I'm going to ask a question to the audience. Hopefully, Jens or someone else will help me as well, because we need to take a fork at this point, decide which one to cover in the remaining part of the talk, because I don't think we'll have time before dinner to cover both. So let me give you both. So processing near memory, you have a processor here, you have a memory here. Today, they're far away. We've discussed this. Why not put processor closer, 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 closer? And the processor could be CPU, GPU, FPGA, or whatever logic that you have, such that it's close enough or integrated together with the DRAM or main memory. So that's similar to the conventional model, except processor gets closer and closer, and it enables a lot of different benefits. It does complicate programming, etc., a little bit. Okay, that's more near term, in my opinion. This is already happening. Longer term, which is a complement to what's already happening, I believe, is you have processor and memory. Processor and memory. Forget the processor. We have only memory. Now, memory, you look at this stores a lot of data. How can I do computation on it now that I remove the processor? Well, this memory has some analog operational properties. Any memory cell can do some operation on the data it stores also. So can I find out what kind of operations I can perform easily without adding logic units into the memory and do those operations in situ inside the memory chip? So this is relatively new. This was not actually thought of as much in the long-term past, let's say. But this enables actually truly in-memory computation, because you can do a lot of logic functions, it turns out, on the data that already resides in memory. Now, this is a different model, clearly. This requires you to rethink your algorithms and programming languages even more so than the second one, processing near memory, requires. Now, I think both of these need to be employed going into the future. And both of these are very different. They can be combined, as we have shown and as others have been looking at. But now I have a question for the audience. We cannot cover both. Which one should we cover? The shorter term or the longer term? I'm happy to cover either one. I don't have a bias against one or the other. I guess I will ask the question, who wants to cover processing using memory, which is analog computation, longer term, a lot more changes to algorithms and programs? Okay, I cannot count fully, but I see a lot of hands. Okay, who wants to cover processing near memory, which is more shorter term? Okay, can someone help?
Das Mikro einschalten?
Yeah.
So, Onur, our timeline is not as strict as you might think. So we can do something like until 7 or so. So that takes a little bit away from our dinner time, but we have plenty of time for dinner. So if we finish at 7, that's perfectly fine.
Okay, I'm not sure if yeah. Yeah, okay. I mean, I saw a lot of hands for using memory, but I don't know if I'm seeing the entire room. Can someone verify?
Yeah, I think it was about 50-50, right?
Okay, wow. Okay, so maybe I'll just continue with using memory then, because I saw a lot of hands, but if you think it's not 50-50, let me know. Okay, so let me just continue then. I think, as I said, both of them are quite interesting, and the second one is already happening. Actually, I'm going to mention processing in memory in the real world. But let's take a look at the longer term one. The reason why this is longer term is there are reliability issues that need to be solved, and also programming of this is not going to be as easy. But the benefits are going to be even higher. Basically, the idea is to take advantage of operational, usually analog operational principles of memory, designed as a memory device to perform block data movement and computation in memory. You can exploit internal connectivity in the memory device to move data, and you can exploit analog computation capability. I'm going to show you both. And who knows what else? There's a lot of creativity and room for innovation over here. I'll start with something simple. I'll cheat. I'll start with data copy initialization. And even data copy initialization is something that we do in our systems today a lot. In fact, Google paper that I mentioned to you earlier shows that only these two function calls, memmove and memcopy, consume 5% of the entire data cycles in their workloads. This is, I think, fascinating, just two function calls, right? Now, how do we do data copy today? If you want to copy a 4 kilobyte page to a 4 kilobyte page in memory, you have to go through the processor. You have no other choice, basically. You have to at least set up the memory controller to do a direct memory access and do the copy that way. Now, wouldn't it be nice if we had a primitive that told the memory, do this copy internally and don't bother anything else in the system? And that's the idea of row clone. This is low latency. I will show you some numbers. This is low bandwidth utilization. You're not exercising the memory bus at all, except for sending a command to memory saying, memory, do this for me. No cache pollution, but you could eliminate that today using direct memory access. No unwanted data movement on the memory bus. You move only what you need. And I'm going to show you a mechanism that takes 1,000 nanoseconds, 4 kilobyte page copy latency to 90 nanoseconds, unoptimized, and 3.6 microjoules to 0.04 microjoules. And the idea is very simple. This is the best case, of course. We have generalized it, but in the best case, the source row and the destination row are in the same DRAM subarray. And let's assume that they're 4 kilobytes. You first activate the source row, which brings the data into the row buffer. These are sense amplifiers. You have to bring the data over there to sense the data first. And then you activate the destination row in the DRAM and implicitly deactivate the source row. Activating the destination row connects the data and the sense amplifiers in the row buffer to the destination row. As a result, you basically copy the data that you copied in the row buffer from row A into row B. By doing basically 2 consecutive activates, you use the sense amplifiers or row buffer as a temporary buffer to move data from row A to row B. And this is negligible hardware cost to do it reliably. In fact, in existing DRAM chips, you can do this by violating the timing parameters. I'm going to show you that. Most DRAM chips already support this, even though they were not designed to support this, and nobody tells you that they support this. You just violate the timing parameters in DRAM when you design your memory controller, and you get a row copy for free. So what are the benefits? Basically, we showed that you get 12x latency reduction in a 4 kilobyte page copy and more than 70x memory energy reduction. And ignore the other bars over here. This depends on where the data is. And we actually propose mechanisms to improve it, but I don't have time to go over those mechanisms. And this is a paper that introduced it. And more recently, folks used our infrastructure that I showed you earlier to show that you can actually violate DRAM parameters to mimic row clone, and you can actually do this in real DRAM chips, which is great, I think. And then we actually built on their work to show that, to replicate basically exactly what they did. And we open sourced and processing using DRAM framework, where you could actually test this with real applications. In this particular paper, we tested row clone with real applications, micro benchmarks. We also have a true random number generation capability inside the DRAM, which I will very, very briefly talk about. But you can download this. You can use it on your own. You can actually make it better because we had limited capability and MAB power. We have a RISC-V system. And to the RISC-V system, we have a modified kernel, modified system calls. You can basically do a mem copy that's specialized to row clone. We call it row clone copy. And that row clone copy gets shipped to the FPGA board, and that FPGA board does it inside the DRAM on behalf of the RISC-V system. As a result, you do the copy much more efficiently. And if you're interested, we have tutorials on this also. And we see actually even higher performance improvements than we reported in our original paper, because by violating the timing parameters significantly, you can do back-to-back activates in a much better way. And you actually improve the performance end-to-end. These are end-to-end micro benchmark results. And we're happy to support it. If people are interested in using this FPGA-based prototype, we're really happy to support it. This prototype also can do what I'm going to show you next in DRAM bitwise operations, but unfortunately, those are harder to do in real DRAM chips because they require more reliability. Okay, if you're interested, there's more I'm happy to talk about. So if you look at this, basically what we're doing is we're thinking of memory as an accelerator. The memory can do some acceleration. It has some great acceleration capability. Why not put an accelerator over there while we're putting lots of accelerators on the compute side? That's the idea. So what else can memory do? And we're going to focus on DRAM chips. DRAM actually can do a lot more. Basically, we showed that it can do AND or NOT functions and a majority function at very low cost by using analog computation capability. And the key idea over here is activating multiple rows concurrently performs computation. I'm going to show you an example. And this leads to significant performance energy improvements in these primitives and other primitives that you can build on top of these. New memory technologies are also very interesting, clearly, and there's a lot of work that goes on. I have some slides on that, but I don't intend to cover them given that we don't have time over here. You can operate on minimal data movement because they're non-volatile. And also they're able to do matrix vector multiplication because of their 3D structure, essentially array structure. That way you can accelerate matrix vector multiplication computations. Okay, let me give you what we can do in DRAM. This is doable in a fraction of the DRAM chips by violating timing parameters. Essentially, we're looking at 3 rows in DRAM, ABC. I'm showing only 1 cell and 1 bit line, but imagine this being 8 kilobytes or 4 kilobytes, whatever you pick, and imagine there being 1,000 or more of these. So you can do these operations that I'm going to show you on 8 million bits or more at a given time in a single DRAM module. So basically, the idea is to activate 3 rows concurrently. If you do that based on circuit operational principles, analog principles again, if at least 2 of the cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. That means that you have a bitwise majority function. So basically, you can do bitwise majority across millions of cells. Now, bitwise majority is nice because if you set C to 1, you get the OR function. If you set C to 0, you get the AND function. Basically, now you have a bitwise AND and bitwise OR at the same time. Now, this is missing clearly a NOT, but NOT is already there, actually. If you look at this picture, the complement of the data that you're reading is actually on the other side of the sense amplifier. And we propose some methods for supplying it back into the array, which I'm not going to talk about. So you can actually have majority and or NOT natively inside the DRAM chip without adding any computation logic. That's the idea. I find this fascinating. It's even more fascinating that some DRAM chips are already capable of doing this by violating the timing parameters very, 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 very carefully, let's say. We call that DRAM chip is not designed or specified for this purpose. Imagine what you can do if you actually design the chip for this purpose. Okay, so what can you actually accelerate with this? Clearly, I believe actually you can write any algorithm to fit this with some pain, no question about that. But there are some algorithms, some applications that are already written to maximize these bitwise operations. And database community clearly knows about bitmap indices. Bitweaving is a database that is written essentially to maximize this. I'm going to show you results with that one. Bitfunnel web search engines have been written with a similar purpose in mind. And there are many, many other examples over here that I'm not going to go into. In the paper, we study bitweaving. We actually port bitweaving to our simulators and show that you can get significant end-to-end performance improvements by doing these bulk bitwise operations inside the DRAM. Again, this is simulated. It's very hard to do in real DRAM chips today because real DRAM chips are not supporting it. Row clone is easy to do in real DRAM chips today, on the contrary. So there are differences here. And you can read the papers for more detail. And this paper actually explains some open questions. For example, error correction is always an open question when you're doing analog computation in DRAM. And that's something that is not completely solved yet, unfortunately. But there needs to be more progress, in my opinion, to enable let's say, error correcting codes and error correction methods for analog in DRAM and in memory computation. This is true for any analog computation, actually, not just what we are proposing. So the problem is actually more general. Now, the question is, how do you make this a little bit more programmable? What we did in 2015-17 timeframe was, okay, we showed that this is possible. How do you make this more programmable? I'm going to give you the basic idea over here. Here in this work, we show that we basically can do any operation as long as the user specifies the operation using and or not logic, gates, let's say. You can specify matrix multiplication, convolution, whatever you want over there. We convert it to majority not logic, and we actually optimize it using tools that were developed by Nani De Michele's group for quantum computing, essentially, to minimize the logic. So we actually turned into majority and not commands. And then we actually generate a micro program that can execute that operation that the user specified. It could be a convolution. And we associate the instruction in the ISA with that microprogram that's stored in the memory controller storage somewhere, essentially. And then when the user actually supplies a program that calls that instruction, again, it could be a convolution. We call it bulk bitwise operation new. That operation gets shipped to the memory controller, and the memory controller invokes the microprogram, which does essentially triple row activation and row clone commands. And then it executes the operation and then notifies the result back to the program. So we have an end-to-end execution model to actually execute any operation. Of course, what kind of performance energy you get from the operation matters a lot. It depends on the operation. For example, if you're doing a 64-bit multiplication, that's not going to perform really well. Why? Because we're doing everything bit serially, 1 bit at a time. So it will take 64 DRAM cycles to do one multiplication. Now, if you can tolerate that latency, that's great, because you're doing this parallel across many inputs. So if you're doing billions of 64-bit multiplications, maybe you can tolerate that latency. Okay, we cover a lot more in the paper, but I'm not going to talk about it. But this framework actually leads to even higher performance energy improvements compared to existing CPUs and high-end GPUs. And we're still working on it to make it, let's say, even easier to program. If you're interested, you can look at our S+ paper from 2021. So there's more that I can talk about in this direction, but we don't really have time. Processing using memory is very interesting. More recently at Micro, it says to appear, but it appeared 1 week ago. We introduced a way of doing these bulk bitwise operations using lookup tables. Some operations are very costly, as I said, multiplication. But multiplication is not that costly if you can use a lookup table to quickly look up the values. And we showed that you can actually accelerate processing using DRAM using lookup tables. We also shown that by exploiting the characteristics, analog operational characteristics of memory, you can build physical unclonable functions. You can identify the device. This is important for authentication and security. You can also generate true random numbers. And the idea over here is very simple. Basically, if you violate the timing parameters when you read a row, when you activate a row, some cells fail. But some cells fail randomly. 50% of the time they fail, 50% of the time they don't fail. And this is a characteristic of the DRAM cell as well as the sense amplifier. So it's a physical phenomenon that leads to true randomness. And if you can actually figure out which cells fail randomly, you can build a true random number generator out of it on the DRAM side. Now, this is great if you're putting security critical applications that need random number generators on the DRAM side. You don't need logic for that. This is not logic, essentially. You just, yeah. And we actually have this implemented in the PyDRAM prototype. So if people are interested in experimenting with it, you can do that. Now, we actually also introduced other methods to do this better, but I'm not going to talk about that in detail. So there's a lot of room for innovation to understand what our chips are really capable of that I believe no one has explored before. They have such interesting analog computation capability to discover, and who knows what else is downstream if you actually look into the chips a little bit more. And these are just design chips, right? We're not even modifying the chips significantly. So of course, end-to-end system design is always important for these things, and we look at a lot of end-to-end system design. Now, more recently, while we were doing the work on DRAM, I was actually quite interested in Flash also, because we had a body of work on Flash. And I always had the hunch that you could do this in Flash. And finally, we gathered together the right group of students who could actually do this together. And in this work, we showed that you could actually do in Flash bulk bitwise computation. So if you actually concurrently activate multiple rows in a single block in Flash, you get a bitwise AND function. And if you actually do the same thing across blocks in Flash, you get a bitwise OR function. And in existing Flash chips, bitwise NOT is already there. You can do an inverse read. So by using the analog computation capability, again, you have a functionally complete system. And in this work, we show that many applications can benefit from it. So I believe actually storage is an even bigger area where you can do these analog operations. You might think that these are slow. Yes, they're slower than what is possible inside the DRAM, but you have a lot more parallelism in the storage device. Plus, what is enabled over here is what is not possible in DRAM as far as we know. You can do a 48 input AND operation, for example, concurrently, all at the same time, with latencies that are similar to 2 input AND operation. And we discussed that in the paper. So if you actually have even higher need for large ANDs, large ORs, and large combinations of bitwise operations, Flash is a better place to do it. And I don't have time to talk about this more, but this is another example of processing using memory, using some other technology. There's more work on emerging non-volatile memories. After our paper was published, these folks showed that you could do what we suggested inside phase change memory as well, but I will not talk about it. And they essentially show the same thing. Emerging memory technologies have in-memory crossbar array operations as well. But again, I'm going to skip this. I think this is very, very interesting too, but sorry, I don't think we can cover things and still take questions if we actually cover this one. But I'll leave these slides online if you have questions. These are some papers that have been early and also very influential in the field, showing that emerging memory technologies have analog computation capability. I believe, as I said earlier, processing using memory is a longer term approach. Even though it's possible to do in some real devices like row clone, that's the step-by-step. If someone actually, it's very easy to implement row clone in my opinion. Once that's implemented, I think people can develop applications that can take advantage of it. But some of the other things require more time to get things reliable, especially the matrix vector computation in emerging memories. It's very hard to make it reliable as you go into larger matrix sizes, for example. Okay, now let me jump into processing near memory, and then I will spend some time, and then hopefully we'll have some time for questions as well. Unless there's a burning question, which I'm happy to take at any point. So feel free to interrupt me. Okay, I should keep going then. It's very hard to see people, sorry. Okay, good. So I'll keep going. Okay, so we're going to keep the same mindset. So actually, I think the mindset can be even bigger also, but we're still keeping the mindset that memory is an accelerator. I think in the longer term feature, memory can be the processor itself also. That's where really things get done. But actually, I think the entire processor needs to be a complete distributed system, and memory should be an equal component of it, just like the CPU. Right now, we're still thinking CPU is the place where things get done, operating system gets executed, and it offloads computation to memory. But maybe that'll change as well. So thinking of memory as an accelerator, what can you accelerate? This is the question that we asked when we were looking at near memory processing early on. And we wanted to look at graph analytics because clearly graph analytics is a challenging application. And one of the reasons it's memory bound is it has frequent random memory accesses, not completely random, but enough randomness that your memory system gets overwhelmed and little amount of computation to cover for it. So to take advantage, so basically to design a graph processing accelerator, we wanted to take advantage of 3D stacking technologies. You have memory and logic 3D stacked on top of each other. In the logic layer, you can put any kind of accelerator. In fact, we're going to put simple in-order cores. And memory layers can house the data very quickly and supply it to the accelerators over here in the logic. And there are other three-dimensional technologies that are under development that are much less constrained. You can mix memory logic, for example. I think these are being experimented with. In the longer term, they're going to be processing immersed with memory. And there's going to be even less limitations in terms of the bandwidth that's achievable in the logic layer and the energy of the data movement between memory and logic. So I think there's a lot more to come in this space. But at the time we were working on it, we were bound by hybrid memory cube, for example. That's one example. And this is the accelerator we designed. This is a full system design. I don't have time to go over every single detail. I'll give you the key ideas. But basically, you have a host processor. It offloads graph analytics acceleration to a distributed system of hybrid memory cubes that look like this. Each of them looks like this, and you have a distributed system, and they're connected using an interconnect. Now, the person who programs the graph analytics partitions the graph, hopefully nicely, so that you get some locality in each of these cubes. Usually, you get some locality. It's not completely random, as I said earlier. And then basically, in each of these cubes, you have a program executing. And that program, each of these cores has a program. It communicates, each core communicates with other cores using remote procedure calls. This is essentially distributed system programming. Whenever you want to update a graph node, you send a message to the core that houses that graph node, and that update happens locally without moving the data. You need to send the temporary values, of course. But it turns out if you do this remote function call-based programming model, you minimize the data movement as much as possible. You're just shipping functions as opposed to shipping data to the functions. And that's basically the key idea over here. There's some sort of interconnect clearly that needs to be good enough internally, and data needs to be somewhat localized so that you don't go off chip too much across these 3D cubes. And the hope is that someone, let's say, dedicated enough will be programming it, because this is non-cacheable. It's like a primitive GPU, if you will. It's physically addressed. There's no virtual memory over here. There's no coherence, basically. Someone needs to satisfy it using their programming model. And we put an in-order core to be able to execute those operations. And there's some prefetching mechanisms that I'm not going to talk about. And basically, we found out that compared to existing systems of the day, this is about 10 years ago, mind you, Tesseract looks different because there is no memory processor dichotomy. memory and compute are coupled together. And then you have a distributed system of coupled memory and compute units. And as opposed to a single node that has a bunch of cores and a bunch of memory, where there's a dichotomy essentially. And as a result of that, you get 8 terabytes per second bandwidth available to the cores, as opposed to an order of magnitude lower, let's say. These are results from 10 years ago. So the numbers have changed and evolved. But today, this number is more than an order of magnitude higher, if you will. And corresponding, the performance improvement is also significant. Averaged across 5 graph processing algorithms, we saw at the time about 13x performance improvement, which I believe is significant. Later works improved on our work. Our work was not optimized enough. And also there are some open questions, like how do you do the graph partitioning? How do you do the load balancing? How do you do the interrupt handling? Internally, we have some interrupt handling mechanism, etc. Later work showed that you could actually increase this to almost 100x, actually over 100x. And the energy improvement we showed was 8x. And later work showed that by improving the system, you could get 100x. And again, this is not a trade-off. Assuming the whole body of work over the course of a decade, you get 100x performance improvement and 100x energy reduction. I think this sounds good. It's within an application, because later work also specialized for graph processing more than we did. We didn't specialize too much for graph processing. Basically, I think it's a good improvement if you actually want to get performance and energy at the same time. There's more, but I'm not going to cover that. Let me give you one other idea in terms of the storage domain. I just want to also venture into storage, because storage is, in my opinion, memory is important, but storage is even more important potentially going into the future, because memory is not going to scale well, whereas storage is going to scale, in my opinion, better. And storage system has a memory system internally as well. So storage system is probably a better place to do the data processing much more efficient. And we've been doing that more recently. I mentioned the Flash Cosmos work, but also specializing for the genomics application. I'll give you the high-level idea. Basically, if you look at the overall system, today we move a lot of data from the storage system. These are reads from sequences, right, going into the computation unit. Now, there's huge computation overhead and data movement overhead, but we actually reduced the computation overhead a lot over decades using heuristics, accelerators, filters. That's true for genomics, but I believe that's true for other applications as well. Mostly ignoring the data movement overhead from storage. We're assuming that the system ends at main memory in many applications. I'm not saying that that's always, but in many applications. But that exacerbates the data movement overhead from the storage system, which is actually even more energy hungry and even more costly. So the idea in this work is to filter the reads, genomic reads that do not require alignment inside the storage system, do some work over there such that you don't put so much pressure on the other part of the system. And that's the idea. I'm not going to go into the detail. This goes into a lot of interesting issues in genomics, and we don't have time for it. But there are two very simple accelerators you can design on the storage system. What is exactly matching the reference genome, if that's the comparison you're making, and what is really far from matching the reference genome. These are easy cases. Do the easy cases on the storage system. Do the hard cases on the computation units, essentially. And if you do that, we showed that you can gain significant performance and energy improvements at the same time, again, at low cost. And the reason there's a huge variation in terms of the speed up as well as energy reduction is because it depends on the data set, the characteristics of the data set. Okay, so let me actually skip this work because we don't have a lot of time. I'm interested in getting questions also. This is a work that we did with Google, as I mentioned, where we showed that you get 60%, more than 60% of the energy spent on the data movement in the memory hierarchy. We analyzed a lot of functions in this work and actually proposed accelerators as well as general purpose processing units near memory to accelerate those functions. Some of the functions are written over here, as you can see. A lot of these functions have very little computation, a lot of data movement. Compression, decompression, that Chrome browser does is an example. Motion estimation that the video decoder and encoder engine does is another example. So there are a bunch of functions you can actually find out that are extremely data intensive. And if you offload them to the memory side, you gain a lot of improvement. And we've been looking at these functions over the course of our research for some time. I'm going to mention some work later on if you have time, but I don't have time probably to cover this one. So there's a lot of other examples that I'm not going to talk about. Let me cover something that is important, which is really adoption. I'm going to skip all of these slides. As I said, these slides were actually for a longer talk, but I'm happy to make these available. So I think the adoption challenges are really the difficult part. How do you get this adopted? In my opinion, I think of processing in memory as something that people can do that like GPUs were 20 years ago or so. right? There are some enthusiasts who were using GPUs. I believe today we have prototypes for processing in memory. If you're actually really interested, you can get your hands dirty in those prototypes and accelerate your applications, see what kind of benefits you get. That's the good part. But these challenges still remain, basically. There are a bunch of barriers to adoption that we need to solve. And most of them are software and system level challenges. What are the applications? What are the software? What is the ease of programming? How do we make it easier? What is the system and security support? What are the runtime and compilation issues? And what are the infrastructures? Maybe more than anything else, the biggest challenge is the mindset, because we have this processor-centric mindset ingrained in ourselves that is just a bit too much, maybe. Now, let me give you an example. So that's why the reason we're doing a lot of this research. If we had time, I would cover more. But let me give you some examples from the real world very quickly. As I said, today we have some processors that can do computation. This is the UpMem processing in DRAM engine. These are real. You can buy them if you want, or you can work with UpMem to get access to them, as we have been doing. So essentially, this is what they have. In a DRAM, next to each DRAM bank, in a DRAM chip, they have a processor. This is a general purpose processor. It's a multi-threaded processor. It has an instruction memory and data memory. Essentially, it's what you would expect from a general purpose system, right? And this is distributed across DRAM banks. Unfortunately, there's no communication between the processors across the DRAM banks. You have to go through the main host processor, which is not a great design decision. But basically, it has its own idiosyncrasies. But we're still able to accelerate some applications. And we have released some workloads. I'm going to mention them, but the more detailed talks are online. You can find them easily. So this architecture is actually very compute bound. It doesn't have a very sophisticated multiplication operation. As a result, you're very compute bound in this architecture. So if you want to get performance out of it, you need to find the functions that are extremely data bound and not compute bound. And even then, we were able to find a bunch of functions. So for example, these are kernels, like these are select operations. And we have some histogram operations, scanning, etc. You can see that we can outperform existing CPUs and GPUs with some optimizations in this system. But there are also some other workloads where this system performs terribly, even with optimizations compared to existing CPUs and GPUs. Well, usually GPUs, but sometimes CPUs also, like general matrix vector multiplication, sparse matrix vector multiplication. These are examples where the system is not very good, basically. So it's a trade-off in the end. You need to figure out which function fits best this system. And the design decisions that are made in the UpMem system are not necessarily the design decisions that you would make if you were actually designing an end-to-end system for your workload, for example. Okay, but there's a lot more. The good news is there's a system out there and there are benchmarks out there, and you can actually experiment with the system. And we'd be happy to support folks if they're interested in working with the benchmarks we have provided. Now, I will also mention that we have done machine learning training on this PIM system, not deep neural network training, because unfortunately, this doesn't have a multiplication operation, a floating point multiplication. It doesn't have an integer multiplication that's greater than 8 bits even. But there are some machine learning workloads like clustering, decision trees, etc. If you optimize them well, this system can accelerate them. And you can see how we optimize them. Basically, you optimize the data representation, lookup tables, data placement, etc. And you get significant speed ups compared to CPUs and GPUs because you can do most of the computation with minimal data movement. I believe these numbers will grow if the system is designed in a different way. Okay, and there are more works that I'm not going to talk about. We will also working on very tough workloads like sparse matrix vector multiplication. There are other architectures. These are not open. I don't know, maybe potentially you can gain access to them if you have connections to Samsung. I don't know. But basically, Samsung introduced processing in memory chips that can do machine learning inference. You can see that this is 3D stacked, high bandwidth memory. And you can see that it has very simple processing units, and they optimize it for a complete different purpose. It's really for floating point 16, multiply and accumulate. So it's not general purpose, as you can see. But this is also real, according to Samsung. And according to them, again, you get good results. You can read their papers that I mentioned in this over here. Samsung and Facebook introduced this recommendation system accelerator, which is essentially this thing over here that plugs into Intel Broadwell. And they basically also report some good results according to their workloads. Again, the goal is to minimize data movement and do the reason they do this in a module is because they need to do a lot of aggregation operations, right? And that aggregation is not easy to do inside the DRAM chip. When you're aggregating a lot of data, it's better to have it in a module, not as far away as CPU, but some buffer basically close to memory. Okay, and then SK Hynix also introduced machine learning accelerators, as you can see. These are all papers you can read in the public domain, but again, as far as I know, you cannot get access to it unless you have some special connections to them. And Alibaba also introduced their DRAM chip that can do recommendation inference acceleration. So I think these examples show that the future is bright. And we've also been working on the questions on what to offload to these accelerators. But again, I'm going to skip that one because we don't have time. Okay, I think this is the end. I will conclude over here. I don't want to spend more time. I've already shown a lot of examples of this. I want to take questions. I believe we need to revisit the entire stack eventually. But more than anything else, in my opinion, we need open minds. If there's hardware out there, we should really be experimenting with it. Maybe even simulators. I know systems community doesn't like simulators that much. We've been doing a lot of simulation work, but maybe even simulators are good to experiment with so that we can enable some of these systems going into the future. I will thank people who have funded us, and I will also thank more than anyone else my research group. And you can see some faces over here who have contributed and have done the research. And a lot of things you can find online. As I said, we open source a lot of stuff online, and we've also organized sessions, so you can find a lot of these things online. We have a lot of courses as well. Let me jump to the back over here, and then I'm happy to take questions.